Welcome to your second video in our Chapter 3 video lectures, where we're going to discuss Section 3.2 on chemical reactions. So we need to first discuss the term metabolism. These are all biochemical reactions in living organisms. So essentially it is the sum of our catabolic and anabolic reactions. When we discuss our chemical reactions, we know that it is going to take place when our chemical bonds in existing molecular structures are broken and new bonds are formed. So we could see this here in this chemical reaction. We have our reactants on the left side and our products on the right side. Our reactants are going to be substances present prior to the start of the chemical reaction, and like we said before, they're written on the left side of the equation, whereas our products, they are formed by the reaction, and we can find this on the right side of the equation. This arrow here is representing our direction of the reaction. In a balanced equation, we're going to see that the number of elements are equal on both sides of the reaction. So on the left here, I have 1A and 1B, and on this side of the reaction, I also have 1A and 1B. So this is a nice balanced equation. Our chemical reactions are classified based on three criteria: whether we have the changes in their chemical structure, changes in chemical energy, and whether the reaction is reversible or irreversible. And we can also classify it based on the changes in chemical structure into decomposition reactions, synthesis reactions, and exchange reactions. Our decomposition reaction shows that we have an initial large molecule broken down into smaller structures. Examples of this would be like hydrolysis reaction of sucrose into glucose and fructose, which you can see taking place down here. And we say hydrolysis because notice that water is involved. Water is added to the reaction that allows the breakdown into these smaller molecules. All of our decomposition reactions in the body are referred to as catabolism or catabolic reactions. So the way you can remember this is by the letter C within catabolism. I want you to think cut. So it's as if we're taking those larger molecules and cutting them apart to get these smaller products. Next, we have our synthesis reaction, and this is when we have two or more structures combined to form a larger structure. An example of this would be dehydration synthesis reaction, forming a dipeptide. So here we have our two molecules, which are amino acids, and notice that we are taking water out. Dehydration, right? We're moving water out. So we are forming a bond between those two molecules, which is a dipeptide. We can use the term anabolism to describe this, and that is for all synthesis reactions. So for the word anabolism, look at the letter A in there and think add. We are adding these smaller molecules to make a larger molecule. And lastly, we have our exchange reaction. These are when groups are exchanged between two chemical structures. It has both decomposition and synthesis components. Most prevalent within our human body, and we could see a simple example of this over here, where we have the molecule AB plus C, and that has rearranged itself to become A plus BC. An example of this would be the production of ATP within our muscle tissue. So on the left side here, we have creatine phosphate, and we are adding that to adenosine diphosphate, meaning di-2, which means we have two phosphates here, and you can see on this creatine phosphate that we have this phosphate molecule. So as the reaction proceeds to the right, we have taken that phosphate molecule off of creatine phosphate and added it to our new molecule, which is ATP, tri meaning 3 phosphates here. And we can have oxidation reduction reactions or redox reactions. This is when we have an exchange reaction where electrons are moved from one chemical structure to another. The structure that is losing an electron has been oxidized during oxidation, and the structure that gains an electron has been reduced during reduction. The reactions always are going to occur together, and electrons may be moved alone or with a hydrogen ion. So an example of this would be our nicotinamide adenine dinucleotide, or NAD+. And we could see that reaction taking place over here. During this reaction, we have our energy-rich molecule glucose, which is not pictured here, but it gives up 2 hydrogen atoms and an electron. So we see that in our NAD+ molecule here, we are going to gain a hydrogen on this carbon over here, and the other hydrogen is lost to its environment. So it just kind of is out there on its own. And now we have NADH. So because we have glucose losing its electrons and releasing its chemical energy, we say that glucose is oxidized. And then our other molecules are reduced because they are gaining both the electrons and energy, as NAD+ is becoming NADH. So once again, just so this is clear, we are gaining 1 hydrogen here on this carbon and an electron, and another electron is going to go over here to this nitrogen. That's why we first have this plus symbol here, and then now because it gained that electron, we are neutral. We don't have that positive charge on this nitrogen. And we said that second hydrogen is just going to the external environment. Now let's move into classifying our chemical reactions. We can classify them as either exergonic or endergonic reactions. Exergonic reactions are when we have reactants with more energy within their chemical bonds than their products do. So notice how on these graphs here, we see that above the 0 on our y-axis is energy being supplied, and below it is energy being released as the reaction continues. So our energy here is being released with net decrease in potential energy. This would be an example of our decomposition reactions. Whereas our endergonic reactions, we see that our reactants are starting with less energy within their chemical bonds than compared to the products. The energy is supplied within a net increase in potential energy. So this would be like our synthesis reactions. And next we have ATP cycling. This is the continuous formation and breakdown of ATP, which you could see illustrated here to the right. Our ATP is going to be formed when energy is released in exergonic reactions. So we could see that we are starting with ADP over here. Once again, di, meaning we have 2 phosphate bonds, diphosphate, right? And when we are trying to turn into ATP, we have that energy that's being supplied. Fuel from molecules coming from our food that are oxidized, and the energy within the bonds transfer to ADP and that free phosphate in order to form ATP. So essentially what we're saying is ADP plus an inorganic phosphate plus energy that we got from our food is going to result in ATP, and this is an endergonic reaction. ATP oxidized to aid in endergonic reactions will result in energy released from ATP to provide energy. We could see that only a few seconds worth of ATP present at a time. The formation of ATP is going to occur continuously in order to provide energy for our body. And we can classify our reactions as irreversible or reversible. Irreversible reactions mean that we have a net loss of reactants and a net gain of products. So essentially, we're only going to one side of the reaction. So A plus B equals AB, or AB turns into A plus B. And a reversible reaction is not only going to proceed to the right side, but it can always go back to the left side. So there's no net change in concentration of either reactants or products. We are in a state of equilibrium, and that is represented by these double arrows over here. We see an increase when there's an increase in our reactants or a decrease in our products, then the reaction is going to move to the right side. When we have a decrease in reactants or an increase in products, then we'll see the reaction drive over to the left side. And we have this term called reaction rate. This measures how quickly a chemical reaction takes place, and it could be affected by activation energy. This is the amount of energy that we need to break existing chemical bonds. And you could see this in the illustration to the right here. Once again, we have that same graph set up where the y-axis is measuring energy and the x-axis is showing us the course of the reaction. And notice how we have our reactant over here. And this is changing based on if we have an enzyme present. So when we don't have an enzyme present, which, by the way, an enzyme is going to speed up a reaction and assist with that reaction moving to the right side. So without an enzyme, you could see that it has a greater amount of activation energy that is necessary. When that enzyme is present, we can reduce the amount of activation energy that is needed for the reaction to take place, and that reaction can proceed much more easily and quickly. So this is a primary factor in determining that reaction rate. We can also do things such as increase the temperature to provide energy to break the bonds. And with the significant temperature increases in a cell, it would do things like denature proteins. So protein catalysts are called enzymes and are used instead.